My name is Melinda Tran, and today I'll be sharing my research internship project on the traversability path navigation for robots. The focus of this work is to program a robot to move reliably within a path and achieve localization without GPS, using simulation as a testing environment. The overall objective is to develop a method that allows a robot to navigate the orchard roads autonomously. Since GPS isn't always reliable under dense tree canopies, I focused on vision-based methods inside the gazebo simulation, which you can see on the right. This simulation provides a controlled environment to test ideas, troubleshoot algorithms, and evaluate performances before bringing them into real-world scenarios. The navigation process mainly involves two phases, tracking the row itself and detecting the end of the row. So today we'll be focusing on state 0 and 1, and we explored this through two different approaches. The first option was using a bird's eye view approach. First, we extracted segmented images from the gazebo simulation. Then, we would fine-tune a pre-existing BEV-former model with our custom dataset, implementing redirection logic as needed so the robot could respond to changes. And finally, the idea was to integrate with a real-world segmentation model in the future. This option emphasizes advanced perception but also requires a significant fine-tuning in order to be reliable. As you can see, we completed the first step, which was to get the segmented images from the front, left, right, back, and top-down view from the gazebo simulation. However, we had issues getting all the information needed to be able to fine-tune the pre-existing BEV-former model, so in the future, we would want to troubleshoot and finish fine-tuning the BEV-former model and connect with the real-world scenario model. Option 2 calculates the traversability path from the front segmentation camera and further calculations. So the second option uses a front-facing segmentation camera that's already built into the gazebo simulation. This camera classifies each pixel into ground, tree, or sky, which is then used directly by the row centering node. This approach is simpler and more direct, since the camera provides exactly the information needed to detect and follow the row. Here's how the row centering logic works. The bird's eye view is divided into 25 vertical slices. In each slice, the algorithm detects path pixels and computes a midpoint. Averaging these gives us the row center line. And then on the debug overlay, you can see that the yellow lines represent the detected row floor, the green lines are the center line, and the red dots are the path sample points. This process also applies an exponential moving average to reduce jitter, making navigation a lot smoother. And then to keep the robot aligned, we use the Stanley controller. This controller corrects both heading and sideways drift, adjusting smoothly with speed for stable steering. This steering command is calculated using both the angular difference to the row and the lateral distance from the center line. Right now, I've been experimenting with tuning the gain factor, which balances the responsiveness with stability. Another key piece of the algorithm is knowing when the row ends. The system monitors the density of tree pixels from the front-facing camera. When the density drops below the predetermined threshold, it assumes that the row has ended. In future work, this will trigger a row switching maneuver so the robot can continue navigating into the next row autonomously. Here is a short demonstration from the gazebo simulation showing the robot navigating the rows, correcting its path, and responding to the row endings. To improve steering smoothness, we refine the control logic with an exponential moving average. This helps balance between responsiveness and stability. A smaller alpha value produces smoother corrections but reacts slower, and a larger alpha value reacts faster but with riskier oscillations. I've been tuning this parameter in simulation to find the best trade-off for this specific scenario. And then to evaluate performance, we use several matrices. First is the cross-track error, which measures how far the robot is from the true center line, and then the row coverage, or the percentage of the row successfully navigated before failure, and then the end of row detection accuracy to see how reliable the system detects row endings. And then we also implemented debugging tools like overlays to help visualize these matrices before testing. Looking ahead, the future works contain finishing the fine-tuning of the BEV former model, implementing a row turning maneuver, building on the prior intern's work, and extending navigation to connect multiple rows, which means integrating an entire pipeline into a real-world scenario. I'd like to thank my mentors Dr. Karki and Dawood, as well as the COWS Lab and Agate for their support throughout the summer.